Alright, before we try to understand that the integral of a rate of change is the net change, let me remind you of the fundamental theorem of calculus. Given proper conditions, the integral from a to b of little f of x dx equals big F of b minus big F of a, and of course big F is the antiderivative of little f. So really, little f is the derivative of big F, sorry. So we could write this in a different way as well. The integral from a to b of big F prime of x dx equals f of b minus f of a. And this makes sense because the integral of a derivative results in the original function. Okay? Now there's more to it than that, but that's the general idea. So now what we're saying in the title of this video is the integral of a rate of change is the net change. So we have some function f. F prime is the rate of change of the function big F with respect to the variable x. So if we integrate that from a to b, what that gives us is the change in f, right? This rate of change, when we integrate it, we get a change in f from a to b. Okay? And so, in fact, this is a net change because at some places over here, when you integrate, this is, if you think about the area under a curve, some of those areas may be positive and some may be negative. So when you integrate that, those positive and negatives sort of counteract each other, and the end result gives you a number, right? The difference between these two things, the value of the function at b minus the value of the function at a, regardless of what's happening in between those, whether the area of under this derivative curve is positive or negative. So it's a net change for that reason. Let's look at a more concrete example. So here I've given a velocity function 2t minus 8, and this velocity is in feet per second, and this is a velocity function for a particle moving along a straight line. So this particle, you know, if you've got this straight line, it can move forwards or backwards, and those are the only two directions it can move. Okay, so that's the idea. Now, I didn't ask a question here because I'll pose two questions now. First of all, determine the meaning of this integral. The integral from 0 to 10 of v of t with respect to time. And what we pick up on is, remember when we looked at derivatives a while back, if you have a position of a particle moving on a straight line and you take its derivative, that equals its velocity. So now if I integrate those two things, then that says the integral of the velocity equals, well, the integral undoes the derivative here, equals basically a position. Okay, so this is very generic here. What I could do to be a little more specific now, though, since we see that v of t is just the derivative of the displacement or the position function, I could say that this equals the integral from 0 to 10 of s prime of t dt. And from what we just looked at with a different version of the fundamental theorem of calculus, this equals s of 10 minus s of 0. In other words, this is its position at 10 seconds minus its position at 0 seconds. So namely what this is, it's a net change in position, otherwise known as displacement. Okay, so we can actually calculate it for this particular function, so that's what we'll do. And we'll keep in mind that this represents its net change in position, its displacement. So we have the integral from 0 to 10 of 2t minus 8, that's what v of t is, and that's what we're integrating. And we want to integrate that with respect to t. Using the fundamental theorem of calculus, I know that has to be the antiderivative of this function evaluated at these values. So the antiderivative of 2t is t squared, the antiderivative of negative 8 is negative 8t, and then we incorporate our constant, and then we evaluate this at our integration limits. So I plug in 10 for this, so I have 100 minus 80, which is 20, plus our constant, minus what we get when we plug in 0, which is just the constant. So we end up with 20, and now we know that's the displacement of this function, and it's positive, of course, we can see that. So it ends up being 20 feet forward of where it was at time 0. So at time 0 it was at a position, and that's actually what this is right here. This is its position at time 0, and this is its position at time 10. We don't know what its position was because of this constant. We don't know exactly where it started, but we know that the difference between those two positions is 20 feet. So now we could ask a different question. What is the total distance traveled? From 0 to 10. Well, now we have to understand that this particle, remember, moving on the straight line can move forwards and backwards. We know that it has a starting position, and we know that 10 seconds later is 20 feet further ahead of where it was, but we don't know if it moved forward and then backwards and then forward again or something like that. So what we have to do is we have to start looking at this velocity. We need to look at when the velocity is positive, and we need to look at when the velocity is negative, and then find the distances traveled on those time intervals. Well, this velocity is right here. If time is less than 4, we have a negative velocity. If time is bigger than 4, we have a positive velocity. So what we're going to do now is, to get our distance, I'm going to take my positive displacement when it's moving only in the positive direction, and then I want to add to that the absolute value of the negative displacement, right? Because I want to consider those to be positive distances as well. And so that's the same thing as, since we have a negative displacement, that's the same thing as subtracting the negative displacement. So we're going to break this integral down. So we've got the integral from 0 to 10 of v of t dt. We'll break it down, since we know we have a breaking point at 4. I'll take the integral from 0 to 4 v of t dt. I know that's going to be a positive number, or sorry, a negative number, because that's when my velocity is negative. So I need to make that a negative value to change that to a positive distance, plus the integral from 4 to 10, and I know that is a positive velocity, so that's already a positive distance. And I'll calculate those two integrals separately, add them together, and that will be my total distance. You should try it out and see if you can get a reasonable answer and interpret it.